Okay, this is going to be a really quick solutions video for the probability assignment task. So if you answered the first question, it's talking about a game of chance has 30 cards that are turned over so you can't see them. Each of the cards has a number on it from 1 to 30 that you can't see. So for 1A, what are the chances of selecting a card that is not 30? Okay, so if we think that we have 1 to 30 in the numbers, I want anything that's just not a 30. If I pick up the 30, that's bad. Okay, so a few people had answered this where they put a 1 out of 30. That would represent the probability of getting the 30. Okay, we want, the question's asking us not a 30, which means 29 out of 30 is the probability of not getting the 30. Okay, so 29 out of 30 will be your question for 1A. 1B, what are the chances of selecting a card with an odd number on it? So if you think there are 30 possibilities, half of them are odd, half of them are even, right? 1, 3, 5, 7, 9, so on and so forth. Those are all odd. 2, 4, 6, 8, 10, those are all even. So it's actually, if you divide it by 2 or by half, you'll get 15. So 15 are odd, 15 are even. So the chances of getting a card with an odd number on it are 15 out of 30. We can simplify that fraction basically just to say 1/2. Okay, so probability of getting an odd number. Okay, I'm showing these as fractions. It's also good if you start to show them in percentages as well. So if we go back to that 29 out of 30, that's 0.96 or 96%, and then 1/2 obviously is 0.5 or 50%. Okay, then for C, cards 3, 7, 9, 12, 13, 20, 23, and 29 are removed. Now what are the chances of selecting a card with the 30 on it? Okay, so now I want the actual card of 30, but I've removed, how many cards have I removed? 1, 2, 8 cards. Okay, so 30 minus the 8 will give us now 22. I want that 30 card, and there's only one of them, so it's a 1 out of 22 chance. Probability of getting 30. Okay, now that I've removed all of those other cards. Okay, and again, we'll show this as a decimal and then as a percent. Okay, so much less chance now, or excuse me, much higher chance of getting the 30. It was 1 out of 30 up here. Now it's 1 out of 22. I have a better chance now. Okay, and then that was C, I think it was the I, and then we have C2. Now what are the chances of selecting a card with a 10 or higher? So we have to kind of look at the ones that have been removed. So I can get a 10, I can get 11, the card 12 was removed, the card 13 was removed, I can get a 14, a 15, 16, 17, 18, 19, 20 was removed, 21, 22, 23 was removed, 24, 25, 26, 27, 28, 29 was removed, and then 30. So if I count these out, like these are all the cards that are 10 or higher. Now that those other ones have been removed, there will be 16 possible things that I can get here out of the 22 that have been left over. Remember, we removed 8 cards, so we're down to 22. So this is the fraction that we're looking at of 16 out of 22. Okay, and if we look at this as a decimal, it'll be 0.72 or 72%. We can actually, we can reduce that fraction to 8 out of 11, which I forgot to do. Okay, so these are your answers for question 1, if that's the one you chose to answer. Remember, you only had to pick 2 out of the 3. So answers for A, B, C1, and C2. Okay, for question 2, we have a 20-sided die that's rolled. What is the theoretical probability of rolling a number 17? So out of the 20 possible options, there was only one that is 17, so that's a 1 out of 20 probability, okay, or 0.05 or 5%, okay, and that's for the probability of rolling 17. All right, that's your answer for 2A. 2B, what are the chances of rolling a number that is a multiple of 4? So if I think of those, right, 4, 8, 12, 16, and a 20. All of those can show up on my 20-sided dice. Okay, that means that there are 5 out of the 20 things that I can roll that would give me that that desired outcome of a multiple of 4. Okay, we can reduce that to just 1/4, which is equal to 0.25, which is equal to 25%. Okay, so those are the chances of rolling a multiple of 4. For C, what are the chances of rolling a number that doesn't have a 1 in the number? So from 1 to 20, 2, 3, 4, 5, 6, 7, 8, 9, they don't have a 1 in it. Obviously when I get to 10 and all of the teen numbers, they're all going to have a 1 in it up until 20. Okay, so if I count those out, there are going to be 9 out of the 20 possible things that I could roll. We can't reduce that fraction anymore. 0.45 or 45%. So I have a 45% chance of rolling a number that doesn't have a 1 in it. Okay, and then D, in an experiment, a student rolled the dice 10 times. Here are the results that they rolled. Okay, so they rolled a 5, 17, 11, 2, 19, 17 again, 4, 8, 14, and a 10. Okay, compare the theoretical probability to the experimental probability of rolling a 17. So we know, back to this question, the theoretical probability of the 17 should have been 1 out of 20. Sorry, my last video got cut off. So we were looking at the theoretical probability of getting a 17, which was 1 out of 20, or 0.05 or 5%, compared to the experimental probability that happened in the experiment where they rolled it 10 times and it occurred twice, so 2 out of 10. We want to compare our fractions with the same denominator, so that's why it's been multiplied by 2. What you do to the bottom, you have to do to the top to give us 4 over 20. So comparing 1 over 20 to 4 over 20, right, it occurred 3 more times out of the 20 than it should have. If I compare my decimals of 0.2 to 0.05, it's 0.15 times more experimentally. Or if I compare my percentages, it's 15% more. So you decide which form it makes the most sense. I'm going to use percentages here, right? So experimentally, 17 occurred 15% more than it should have. Okay. So important questions when you're comparing theoretical to experimental. And then lastly, E. A 12-sided die was rolled immediately after the 20-sided die. What are the chances of rolling the 20-sided die and getting a number with 2 in it, and then rolling the 12-sided die and getting a number with a 2 in it? So I'll show you just quickly. 7, 8, 9. We're going to run out of space here, but that's okay. 16, 17, 18, 19, 20. Okay? Really hard to see, but that's from 1 to 20. So they're looking for the chances of rolling the 20-sided die, right? This is the 20-sided die, and getting a number with a 2 in it. So that's 1, 2, 3. 3 numbers have a 2 in it. Okay, so my first fraction will be 3 out of 20. And then I'm rolling a 12-sided die immediately after. So what actually happens here is each roll has a 12-sided die written after it. Okay, and if you did 12, because there's going to be 12 options for every single one of these 20 options. If you did 20 times 12, you'd end up with 240. I don't have the space to be able to draw 12 options for each one of these numbers. Okay, so I'm just going to focus on the ones that I'm concerned about. So let's say I roll a 2, right? 10, 11, 12, okay? And I go from 4, 5, 6, 7, 8, 9, 10, 11, 12, okay? So I roll the 2, woohoo, that's one of the ones I wanted. And then I wanted to roll a 12-sided dice, and I'm looking for another number that has a 2 in it. So if I look here, I've got 1 and 2. 2 of those options, 2 and 12, are available, right? So let's just look at here, right? 2 and 12 are the ones that I want, and here 2 and 12 are the ones that I want. So 1, 2, 3, 4, 5, 6. So if we had one of these tree diagrams happening for every single number, there would be 240 possibilities that would come out, all looking like this for every single number. We'd only want 6 of those to happen, 6 out of the 240. Okay, so another way that you could have calculated this, I'm kind of showing it through this, is actually using this fraction and one of these kind of tree branches. So if you look here, this was a 2 out of 12 probability, right? I can actually multiply these numbers. So 3 out of 20 was the first set, times, and then this represented our 12-sided dice, times the 2 out of 12 that we wanted, right? The numbers 2 and the number 12 had a 2 in it. So I take that first branch and I multiply that fraction by the second branch. You would get the same answer as what you have here. Okay, it's a 6 out of 240 probability. So whether you count all of the final like branches that happen on this line, this is the final one of the outcome, or if you just take one part of it and this part of it and multiply them together, you'll end up with the same answer. Okay, this can actually be reduced to a 1 over 40, and then we can represent it as our decimal and as our percent. So if I wanted to roll the 20-sided dice and get a 2, and then roll the 12-sided dice and get a 2, I'd have a 2.5% chance of that happening. So not very high at all. Okay, so that's for question 2. And then lastly, question 3. A bag of marbles is placed in front of you. You're told that there are 10 yellow, there are 8 red, 7 blue, 4 green, and 3 purple. Okay, so question A wants us to calculate the theoretical probability of getting each one. So if you add up, remember, theoretical probability of each color is that desired outcome from the total outcomes. So I need to know how many marbles there are in total to figure out what the denominator of that fraction will be. And when you add those up, it'll be 32. So for yellow, our probability will be 10 out of 32. Okay, and then you can look at these, that can be reduced to 5 over 16. It can be represented as a decimal, and it can be represented as a percentage. So pretty good percent for getting a yellow. If we look at red, red will be 8 out of 32, which is a 1 in 4 chance, 0.25, or 25% chance. If we look at blue, blue will be a 7 out of 32. Can't reduce that fraction anymore, 0.2187, or 21.87%. Green will be 4 out of 32, which is reduced to a 1/8, or 0.125, or 12.5%. And purple will be 3 out of 32, same thing, that can't be reduced, 0.0937, which will be 9.37%. Okay, so these are all the theoretical probabilities for getting those colors in the marbles. All right. Okay, so B asked, what are the chances of getting a marble without the letter R in its name? So if I think yellow, yellow doesn't have an R in its name, so that's going to be 10 marbles I could get. Red, that has an R. Blue, that doesn't have an R, so we'll add that into the possibility of the ones that I want. Green has an R, purple has an R. Okay, so just yellow and just blue, which will give us 17. So if I wanted to get a marble that didn't have an R in the name, that's a probability of 17 out of the 32. Okay, probability of not getting the R, we'll just call it that. Okay, and if I look at that as a decimal, it'll be 5312, or 53.12%. Okay. C, in an experiment, a student picks out 10 marbles. Here are the results of what they've got. So red, red, purple, green, blue, they got another green, they got another blue, they got another red, they got another green, and they got another blue. Okay, so here we're going to compare the theoretical to the experimental. So remember, it's not enough just to be like, well, they got 3 out of the 10. You have to compare it using either the fraction, the decimal, or the percent. So let's look at red. Red, and we'll call this the theoretical probability of red, was supposed to be a 1/4, a 25, a 0.25, or 25%. And then experimentally, the red occurred 3 out of the 10 times. Okay, and if I look at those now as decimals as well, 0.3 or 30%. Okay, so in this case, right, 30%, that's greater than 25% by 5%. So red occurred 5% more than it theoretically should have. Okay, let's look at the theoretical probability then of purple. Purple should have been, we'll just use percentages in this case, 9.37%. Okay, compared to the experimental probability of purple, which was 1 out of 10, or 0.1, or 10%. I would say in this case, if we kind of look at these two, 9.37 compared to 10% are very close actually. That percentage, I would say, would be pretty accurate. So we can even write that. We can say very close. Okay, I'll just look at another page here. So let's look at the theoretical probability of green. So green was supposed to happen 12.5%. Okay, according to our numbers up here, 12.5%. And experimentally, green occurred the 3 out of 10, 0.3, or 30%. So when I compare these two, 12.5% is much less than 30%. Okay, what will it be? 15, 16, 17.5, right? So 17.5% difference. Yeah, so it occurred way more than it should have if we're thinking about theoretical to experimental. Okay, and then lastly, theoretical probability of blue. Theoretically, it should have been 21.87. And then experimentally, blue happened, again, 3 out of 10, 0.3, or 30%. So looking at these two, 21.87% is less than 30%, right? Theoretical to experimental. So it occurred, again, more than it should have. It occurred 8.13% more. Okay, so this is how you can kind of compare theoretical to experimental using one of the values, the fractions, the decimals, or the percent, whatever makes the most sense for you. Okay, and then lastly, we have a D question. So the 6-sided die is rolled immediately after picking out one of the marbles. What are the chances of picking out a marble with 5 or more letters in the color name? So if I think of the marbles that I have available to me, yellow, that has 5 or more letters. Red does not. Blue does not. Green does. And purple does. Okay, so that's going to give me 17, right? There's 17 out of the 32 options. So if you wanted to look at this like a tree diagram, nine, 10. What was the 4? 4 was green, 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 and then purple, right? Purple, purple, purple. Okay, so here's all the chances of getting something that has the colors I want. Obviously, we'd continue with the rest of them, and that gives us the 17 possibilities. Like there would be red here, red, red, and there'd be blue, blue, blue. Okay, out of the 32 possibilities of those. We want to know what are the chances of getting one of those with 5 or more letters and then rolling a die and getting an even number. Okay, so 1, 2, 3, 4, 5, 6. That's what we're rolling our 6-sided die. Even numbers are 2, 4, and 6. So there's 3 things here, 3 out of the 6. So if you remember back to the previous question, there's 2 ways that we could do this. We could actually draw this out for every single one and figure out how many of the options we would want. Okay, if there was 17 here and there's 3 that I want, you do your 3 times 17, and that would get you that 51. So 17 times 3 equals the 51. Okay, but what we're actually going to focus on is multiplying those 2 fractions to figure out how many exact possible outcomes there are. So 17 over 32 times the 3 over 6. That's going to be us the 51, right, which is what we said we were looking for. And then it's going to tell me how many possible things could happen, though. So 51 out of 192. If for me to get a marble that has 5 or more letters in its name, and then to roll a dice and get an even number, okay, those things happen consecutively. We got to figure that out. So that's that 51 out of 192. It could equal the decimal, or it could equal the percent. Okay, but here's your probability of getting that letter with 5 or more, the marble with 5 or more letters in its name, and then rolling an even number in a dice, 51 out of 192. Okay, hopefully you can check your answers on these questions, and then if you have any further questions, just email me and I'll help you out, okay? Thanks.